This is a problem from chapter 23, number 12, series circuit. It says for a series circuit of A3 identical light bulbs, each of resistance 4 ohms, and a voltage source that provides 6 volts, compute the total resistance and the total power output. Then, for a series circuit of B3 different resistors with resistances 50 ohms, 30 ohms, and 20 ohms, and a voltage source that provides 100 volts, compute the total resistance and the total power output, and then in the process derive the formula for adding resistances in series and Kirchhoff's loop rule. Now, as far as adding resistors in series or in the next problem in parallel, our book isn't really doing that, but I decide that it is important to do it, so I made up these problems, and you will have to become familiar with the formulas for adding resistances in series, which is simply adding the resistances, and adding resistances in parallel, which you will see is adding the reciprocals, but that'll be the next problem. Okay, so for this one here, it would be a circuit that looks like this. This would be part A. So there we go. 3 identical light bulbs. Oops. And actually I noticed that on the last one I put, on the applet, I put an ammeter there, so I'm going to put that here too, except that wasn't drawn very nicely, so there we go. And here's the battery, and it says 6 volts, and then it says 4 ohms, 4 ohms, and 4 ohms, and again, that's just my handwriting here. That 4 didn't look very nice. 4 ohms there. Okay, and now it says compute the total resistance and the total power output. Well, I figured let's go to the circuit over here first, to the one that we can build, and do it right here. Take this resistor out and put the light bulb back in, except I need more light bulbs and a little bit more space. Yep, that's fine, but I also need to change the resistance here. That was 4 ohms. I actually do need even more space. Okay, that would be actually moving it out of the picture. There we go. I'll tell you later why I need more space. Okay. 4 ohms, and again I want to show the value. I actually decided to kick down the battery's internal resistance to 0.0 ohms because otherwise I would have to round numbers left and right, and I think that would make it more confusing. So I'm just going to leave it as 0.0 ohms, so there won't be any rounding involved. Actually, let me move that resistor out of the way here. Alright, I need 2 more wires. Oops, careful. There we go. And there we go. Okay, and then I close the... Oh, that is bright. Okay, I forgot something. There was the old circuit for the resistors at 100 volts. So I just want to have it at 6 volts here. And now much fainter. I actually compared this one to the circuit we had earlier with just a simple circuit, and notice that each of the light bulbs is actually fainter when they're all in series. We can simulate just the one light bulb again. I think all I have to do is just take two light bulbs out of here and notice what happens now. Okay, relatively bright, this one light bulb here, but notice if I put all three of them in series, then they're quite a bit fainter. Okay, so what we get here is a total current of 0.5 amps, and we have a total voltage of 6 volts, and so we're going to get a total power of 3 watts, 0.5 times 6, so 3 watts. That was one of the questions that was listed in there. Let's see, the other question was, compute the total resistance and the total power output. So we're actually halfway down here. Let's see the total resistance. I'm going to turn this off here for just a moment. So each of these here has 4 ohms, and I come up with 6 volts and 0.5 amps, as we saw a moment ago. Well, if I use Ohm's law, then I would say 6 volts divided by 0.5 amps, which is 12 ohms, is the total resistance. And that actually answers a follow-up question which says that, what's the formula for adding resistances in series? Well, 6 volts divided by 0.5 amps is 12 ohms, and when I look at the individual resistances, 4 and 4 and 4 is of course 12 ohms as well. So that pretty much answers all the questions that are listed there, but let's do it on paper anyway. Okay, oh, this is the FET team here, I guess, some of them. Physics, Education Technologies, but I meant to go there. There we go. Alright, so 3 each in a voltage source, compute the total resistance and total power output. Okay. Actually, I will turn to the book here, which says on series circuits, among other things, that electric current has only a single pathway through the circuit. This means that the current passing through the resistance of each electrical device along the pathway is the same. That means the 0.5 amps that we saw is running through any one of those resistors. I will go back in a little while and show you that in the simulation. And then it also says that the voltage drop across each device is proportional to its resistance. Ohm's law applies separately to each device, and so that means that the voltage drop on each one of these here is the same and equivalent to each resistance. That's also why it shows equal resistances across here, so each one of them is 4 ohms. There are 3 of them, so they have to share the voltage, so each one of them gets 2 volts of that voltage drop of 2 volts. And then the current that flows through here, well, I calculate that in just a moment. For each one of these here, Ohm's law applies separately, so it's current equals voltage divided by resistance, which is 2 volts divided by 4 ohms, which is 0.5 amps, and of course they're all the same here, so my calculation goes for any one of them. And then it says in here the current is the same running through all of them, so through each of these here it's 0.5 amps running through here. Okay, then the total power is the current times the voltage, Well, the total current is 0.5 amps. The total voltage is 6 volts. Again, it's 2, 2, and 2. And that one then comes out to 3 amp volts or 3 watts. Okay, it says here, in the process derive the formula for adding resistances. Well, if we look at this one here, Ohm's law again, for the total, these here are for the individual ones. So this one here was for the individual ones, but now it's going to be the total. So total equals total voltage divided by the what is called the equivalent resistance. I need to push this over a little bit. Well, I have 6 volts, of course, as the total. And I divide that by the equivalent resistance, which is 12 ohms, 4 plus 4 plus 4. And that is indeed the total current of 0.5 amps. Okay, now here the 12 ohms, where did I get that from? Well, the equivalent resistance in series is add the resistances just the way they are, which is 4 ohms plus 4 ohms plus 4 ohms, and that is a total of 12 ohms. Okay, let me just go back to the simulation, and it said something in the book of that the current is the same going through each one of them. So let me show you that. It's 0.5 amps is the total current, and I need to split the junctions here, and there are 2, and then I put the piece of wire there, and I put this one in here, hopefully. Oh, I have to shift this down a little bit. There we go. Didn't quite do it. Maybe. I think now it did it. Okay. Alright, 0.5 amps going through this lamp here, and you probably can believe that that would be the same thing over here. As far as the voltage on each of these concerned, I just introduced a voltmeter, and I'm going to hook it up here, and it reads 2 volts on this light bulb, and it reads, no, not 4 volts, that's the 2 light bulbs together, but 2 volts on this light bulb, and then it reads 2 volts on this light bulb. So indeed they're splitting up the voltages proportionally.